Welcome to Ghostlike's channel. I am his AI assistant, Vilo, and I will be responsible for the audio information streaming into your ears in this next mini-series on microservices. In the previous ones, we disposed our authentication concerns and now know how to build a login page. We now know how to configure Azure AD for it, how to use the MSAL library to get the token, how to plug the middleware on the backend side, and how to use the IndexedDB to store the user information in a non-blocking fashion on the browser. In this series, our focus will move towards making our applications unboundedly scalable. Towards that end, we will go back to one of our old projects and redesign it as to make it scalable. Remember this poker app that we made? The last time we touched it, we showed how to deploy it to Azure as a web app. While we were successful in that particular task itself, it didn't leave a great aftertaste in our mouth after it was done. The reason being that while the app we have made is perfectly fine as a local application where the browser just serves as the UI, it is not a scalable web application. The problem is how we are using WebSockets on a stateful server. And by stateful, we mean that the backend server is keeping the player model in its memory. And these two things in combination are preventing the application from being scalable. Let us diagrammate what we mean. Suppose a single user types in the URL and connects to the server. Since we are doing it over a WebSocket connection, what happens is that he sends a HTTP request, which then gets promoted into a WebSocket connection, which establishes a bidirectional channel between the server and host. If there is only a single user, there is no problem at all, but more users can come. Keeping idle WebSocket connections is no problem, but if the server's computational resources become occupied, that means the other users cannot be served. This is easy to demonstrate on our own app. We'll open a few tabs to show what happens if we try training in tandem. Sorry about this. What we expected would happen is that each of the requests would have to wait until the previous finished, but as you can see they are trucking along in parallel. For the purpose of this narrative, the Elmish Bridge library is being too convenient. Let's see how far we need to go in order to strain the server. Anyway, as you can see, it doesn't really take too much to strain the server. If more than 4 users try running the training in parallel, the machine will start to struggle. Our own machine has 4 cores, so it makes sense that at around this point is when the CPU starvation would occur. Ideally, in such situations, what we would like is have users be served by different servers. The big problem is that the established WebSocket connections to one server cannot be simply transferred to another. So those at the back of the queue will simply get stuck waiting until those in front finish. This is why in general you'll hear that WebSockets are not scalable. With regular HTTP requests, the machine will get one, do its processing, and then go idle. If the machine is in the middle of processing, then the user isn't necessarily stuck waiting until those in front finish. Rather, his request could be routed to another. And that is why regular HTTP communication is considered scalable. But WebSocket connections have their advantages. For example, instead of the request-response cycle, since there is a bidirectional channel, the server could send updates to the user on how the training is proceeding. This kind of asynchronous communication would be impossible with regular HTTP. Also, HTTP requests are expensive. The HTTP header needs to be parsed and inspected on every request, and potentially, the token validation would require running expensive cryptographic functions. The server itself might also need to contact the token issuer, such as Azure AD, in order to validate the token. Having to do that on each and every request is computationally demanding. WebSockets don't have that problem of needing to do needless work on each and every message sent. So we'd like to have the scalability of HTTP communication and the efficiency and flexibility of WebSockets. The way to scale WebSocket connections is pretty simple. The proxy could, for example, authenticate the requests before routing the requests to various serverless functions on the cloud. As for those serverless functions, since they could be configured to only get requests from the proxy which has already authenticated the user, they would not need to do that again, saving them the expense. Our own machine struggled when it came to training more than 4 agents, but if it merely acted as a router, it could serve a far larger number of concurrent connections. And that is the way to make WebSockets scalable. In the real world, what you will observe is that the cloud providers have API gateways that serve that exact role of authenticating the user and routing the requests to further relevant services. And if we check their pricing, we'll see that WebSocket connections are much less expensive for the reasons we noted. This architecture of having a big router or gateway in front, which calls out to various serverless services, is called the microservice architecture. That should be good enough for an introduction. We've checked, and unlike the AWS API Gateway, Azure's equivalent, that is API Management, does not support WebSockets in serverless mode, so we'll set up our own web app to serve such a role, like in the diagram we showed. We'll try out the API Management with HTTP requests in a future video. In truth, we are not really sure how configurable they are, or whether they'd be suitable for everything we have envisioned, and experimenting to find that out is something we will be doing. In the next video, we'll start out in a very simple way by setting up an Azure Function app template. What we wanted to do is just dive into our old project and get it ready, but it would be a mistake to do that before we are familiar with the capabilities that serverless functions offer us. We'll do some research to get familiar with the basics, and only when we feel ready will we start converting our own project to serverless. Please like and subscribe, and get ready for the next video. It will be out soon.